Let's do some more asymptotics examples. These are fun. So I wrote down the main theorem we have here. Again, if we have certain conditions holding for our function, then we get an asymptotic result for the coefficients of our generating functions. Let's do an example that we've seen in the past. So let an be the number of two regular graphs on n vertices. So on n labeled vertices. We've seen, using the exponential formula, that the sum, n going from 0 to infinity, of an over n factorial x to the n is equal to e to the negative x over 2 minus x squared over 4 divided by the square root of 1 minus x. So let me call that function f of x. So the idea is to identify the singularity of your generating function nearest to 0. And that's going to dictate the asymptotic behavior of your coefficients. Here, the only singularity is at x equals 1. So I'm going to consider the following. I'm going to look at the limit as x goes to 1 of 1 minus x to the 1/2 power, so the square root, times f of x. So if I multiply by 1 minus x to the 1/2 power, is going to cancel with this term here causing the singularity at 1. So I'm going to remove the singularity. And if I do this limit and take x equals to 1, I believe I get e to the negative 1/2 minus 1/4, which I guess is e to the negative 3/4. That is my value c in the statement of our main result. So here alpha is, maybe I should be super clear about it this time, alpha is 1/2. R is equal to 1. And c is equal to e to the negative 3/4. So thus, an, I really care about an. I don't really love an divided by n factorial. So an over n factorial, I'll deal with the n factorial in a second, is asymptotic to e to the negative 3/4 power n to the alpha minus 1 power. Alpha here is 1/2, so this would be 1/2 minus 1 power divided by gamma of 1/2, which we've calculated earlier, times r, which is 1, to the n plus 1/2 power. So what I really am interested in is an. An is asymptotic to e to the negative 3/4 power n factorial. So I'm going to multiply by n factorial to get an asymptotic formula for an. I have a square root of n in the bottom, the denominator, and gamma of 1/2, we've seen, is the square root of pi. So this is nice. This is nice. I can go one step further, however, because I have an n factorial, and I can use Stirling's approximation. So this would be n factorial 2 pi n, n over e to the n power. All that's divided by, let me put the e to the 3/4 on bottom since there's a negative exponent, and I have a square root of n pi. So the n pi's can cancel, and I'm left with the asymptotic formula, the square root of 2 n to the n power divided by e to the n plus 3/4. So that's a really interesting result. The number of two regular graphs on n vertices is approximately this quantity. Very nice, very nice. So we got that pretty quickly from our investigations with the main result in asymptotics. All right, let's do another example or two. So here's one more example for this video. I think I'll do one more video after this with even more examples. So let's suppose I define a sequence an by the generating function n going from 0 to infinity of an, and this time I'm going to also include x to the n over n factorial. My generating function happens to be 1 over cosine x minus sine x. So this is actually a combinatorial sequence that you could define in this way. It's known as the Springer numbers. You can look them up on the online Encyclopedia of Integer Sequences and see what they count. But for now, let's just play with our asymptotics results and find an asymptotic formula for the coefficients an. In this case, I have singularities whenever I have a division by 0. So I have a singularity whenever sine and cosine are the same. So my singularities are at pi over 4 plus integer multiples of pi. The r that I need to take in this theorem, because of condition 1, needs to be the smallest singularity I find. And in this case, pi over 4 is the smallest, the closest to 0. So my r, when I'm investigating the asymptotic behavior of this sequence, is pi over 4. So now let's see this. So we see that the limit as x goes to pi over 4 of pi over 4 minus x times my function. Now, the bottom has limit 0 almost by construction because I'm finding a singularity. I'm finding where I'm dividing by 0. So this tends towards 0 as x goes to pi over 4. And the top does too. The top goes to 0 as x goes to pi over 4. So I can employ L'Hopital's rule to take this limit. If I employ L'Hopital's rule, I take the derivative of the top and I get negative 1. And the bottom becomes negative sine x minus cosine x. If I actually evaluate this, I have no problem plugging in pi over 4 at this point. So I have essentially removed the singularity at pi over 4 by multiplying by this quantity. If I take the limit and plug it in, I think I will get 1 over the square root of 2. So that is my c value that I find in statement 2 of this theorem. Okay, thus I've removed the singularity at pi over 4. The next smallest singularity is not at pi over 4. So I could use the theorem, and we have that an, actually let me write it this way. I have the coefficients of this function being asymptotic to whatever. In this case, the coefficient is an divided by n factorial, just like the previous example. But I'm going to write it as an as asymptotic to n factorial times this result. So I'm going to multiply both sides by the n factorial, just like I did in this example, so that I could use Stirling's approximation in a minute. So anyway, I get an is asymptotic to n factorial. The constant c is 1 over the square root of 2. I have n to the 0 power. Alpha, in this case, is 1. That's the exponent I needed to cancel out the singularity. So in this case, alpha is 1, so I don't have any n power. I'm dividing by gamma of 1. Gamma of 1 is equal to 1. And I'm also dividing by 1 over the r, which in this case is pi over 4, to the n plus 1 power. And there is my asymptotic formula for the coefficients, an. I can, as mentioned earlier, I can use Stirling's approximation and I can simplify the n, or simplify, I could write the n factorial. I'm not sure it's simpler, but I could write the n factorial as asymptotic to 2 pi n over e to the n power. I'm dividing by the square root of 2. And actually, let me write this part as 4 over pi to the n plus 1 power. So this is nice. I can beautify this a bit if I want. I can cancel the square root of 2's. And I also have 1 power of pi I can factor out. I don't know. You can make this look nice if you'd like. Maybe I'll write it as 4 to the first power times the square root of n divided by pi times 4n. So I'm grouping the 4 to the n power into this exponent of n. 4n divided by pi e to the n power. So that's a really cute answer as well. The formula involves pi times e to the nth power. I don't know. I like these kinds of things. Okay, I'm going to finish the sequence of videos on asymptotics examples with one more video. So please follow me along there.